Okay, welcome to Physics 1. This is Lecture 1. It is hopefully going to be a series of lectures covering all of the intro level Physics 1 university level courses. This should cover both algebra and calculus base. There'll be some indications on what you need to know as we go throughout the videos. I'm your instructor, be Andrew Knudsen. I'll be walking you through this, and we'll just go ahead and get started. So whenever you do an intro course, I don't know where everybody is, if you've had these courses in high school, or if you're just starting out, or if it's been a long time since you have done any type of education learning. So I want to make sure that this is the absolute basics. Okay, so I'll start you off on ground zero, and we will build from there. So if you do find the first few lectures to be kind of boring, I'd hopefully make them a little informative and fun, but hold on, because it will get more complex as we go. Okay. And so the first lecture is based on units and measurements. And it starts off for a reason. Like all other sciences, physics is based on experiments, observations, and quantitative measurements. So if anything is misunderstood, we always do experiments and determine why or what is causing that, and that's how we get everything. All of our knowledge grows from this. So we do these experiments, we observe, and we take measurements. So it's very important that we actually start with this, because this is how physics and a lot of other sciences come to be. So how are we going to take these measurements? Okay, we have three standards that we'll use, and it's the standard unit. These came about in 1960. It was an international committee that established these sets of standards. It's for all fundamental quantities of science. They call them the SI unit. It stands for System International. It's a French system, and it goes over the fundamental units for length, mass, and time. Those are the three that we're interested in right now, is length, mass, and time. There are, of course, other ones that also have SI units that we can discuss later on in the course, in other courses, for instance, like temperature being the Kelvin, current being ampere, or the amount of a substance being the mole. Okay, but for now, we're going to just assume that these three are our main ones for starting. I don't want to overdo it. And we'll start off with length. So we measure length in meters. So you might see it written out as meters, or you might just see it as a lowercase m being abbreviated, or you might see it in the other writing METRE, depending on what your book is. So I'm going to go into kind of like a little history on the meter, on the length unit. This is mainly just to kind of give you a background on what was happening with it. The definition of length, of course, is the distance between 2 points. Okay, any distance between 2 points would have a length in a space, either a 1D, 2D, or a 3D space. So let me take you all the way back to the origins of this and kind of where these units came from. 1120, the King of England at that time had decreed that he was going to make a standard length, his country-wide, and he would call it the yard. And it was going to have to be precisely equal to the distance from the tip of his nose to the fingertips of his outstretched arm. And that is what he decreed to be a yard. And then everything in that kingdom was measured out through the yard due to the king. Similarly, you had the same type of scenario happen with the standard for the foot. That was by the French, and it was the length of the royal foot of one of the King Louis. Neither of them, however, are consistent. As kings die out, new kings take over, or countries are divided or overtaken, and they end up under new rule. All of a sudden, all the lengths change. Okay, so this stayed kind of their standard until right before the 1800s, 1799. At that point, they decided to redo it as a new legal standard of length in France, and it was known as the meter. At the time, it was defined as 1/10 millionth of the distance between the equator to the North Pole, along one particular longitudinal line that passed right through the heart of Paris. It was much more scientific and it didn't change. However, there still were some concerns. It was an Earth-based system. For one, you had to understand Paris. It wasn't universal wide, and it was difficult to measure. So it didn't really satisfy a lot of the requirements that were needed in the scientific community. In 1960, that was changed now to the length of a meter being defined as these two scribed lines that were on a platinum iridium bar that had been stored under controlled conditions in the heart of France. So that kind of eliminated some of the need to know what was quite going on, the length of Paris to here, and it allowed people to come and copy what they deemed to be a meter. But again, you still see kind of where there could be some error in that. Just a little bit off, and then you make another copy of that copy and a copy of a copy of a copy, and pretty soon you're actually off by a decent amount on your version of a meter. So we still needed some work. That went on until I think late 60s, early 70s. Then the meter was redefined yet again. This time it was more of a scientific approach. They looked at the wavelengths of the light that was emitted from a Krypton 86 lamp. That lamp produces wavelengths with a specific period. If you looked at that and you counted up like around 1.6 million of those wavelengths, that's then what they deemed to be a meter. And it was more scientific. It was 1,650,763.73 wavelengths. It was very, very accurate. It was close, and you could reproduce it in a scientific lab. You could have it, and it was more of a scientific, and it was Krypton, so it was more of a universal measurement. Excuse me. Of course, we wanted something more precise, something much more easily obtainable. So what we ended up doing, it was kind of arbitrary that we had picked Krypton 86 to be our representative for what a meter was. So October 1983, it was defined yet again, and now it is in its current state. So we've gone from 1983 to the shooting of this video, 2025, with it being in this state. And who knows, maybe later it'll change yet again. This state has now defined the meter to be the distance of light, distance traveled by a beam of light in a vacuum, in the amount of time of 1/299,792,458 of a second. Now, again, these are all numbers you don't need to know, not specifically from my class. They're more just for yours. But that number alone, that number specifically stands out because that is the speed of light. 299,792,458 meters per second is the speed of light. So 1 over that gives you precisely 1 meter. Okay. So, and then this makes it a little more universal, being that the speed of light is something that is very fundamental, and it is believed to be constant and the same everywhere throughout the universe. And that any advanced civilization would need the speed of light in their calculations to be able to do space travel, to do, to further along their civilizations. Any type of a science background would involve the speed of light. So this is really cool. We were able to go ahead and get meter defined very, very, very precisely. It took a lot of renditions, and again, it was pretty recent. 1983 was, 40 some years ago. And we were still not sure what we were doing with the meter. It's kind of interesting to think. So that's how we came up with the meter. Some examples of a meter, if you're not too familiar, you can see in the picture located on the screen there that about 1 meter is just over 3 feet, 3.26 feet. If you're used to a foot being the U.S. customary unit, so it's a little bit over a yard, which is also equal to 3 feet. Or you can kind of step it out on the floor and see about what a meter is. Okay? And that's the units we're going to be covering. So when we do say things In our class that move with a certain move a distance of 10 meters, this is kind of a visual representation of, okay, I think that's about 30 feet if that's the unit you're accustomed to. There are other ways of measuring meters. For instance, if you look at the radius of the Earth, the radius of the Earth is about 6 times 10 to the 6th meters. So we're using scientific notation for that one, 6 times 10 to the 6th. Or you can measure things very, very small if you wish, using scientific notation. We'll talk about scientific notation here in a little bit as well. For instance, like the diameter of a proton is about 10 to the negative 15th meters. Very, very, very small. So meters can be we can use them in very large applications, like the Earth to the nearest galaxy, Andromeda. Okay, we can measure that in meters. It's about 2 times 10 to the 22nd. All right. So anyway, meters works very, very well. It's not too big, it's not too small. We can move it around and get mostly all of our measurements done with meter. Mass is our second one. I wish this one had a much better history or a background, but it's I don't find it to be specifically as thrilling as length. The SI unit for mass is the kilogram. You'll see it written out as kilogram, or you might see it abbreviated as the lowercase kg. It's the mass of a specific platinum iridium alloy cylinder, and it's at the International Bureau of Weights and Measures in France. You can see a picture of it there in the glass cases. It is this platinum iridium cylinder sealed away. And that's what we refer to as mass, and we still do to this day. It was originally established in 1887 and hasn't changed since. We're still looking for something else to replace it, but nothing else has come along that is universally accepted. It is noting that there is a duplicate, of course, at the National Institute of Standards and Technologies, or NIST, in Maryland. And mass has the same value as these various objects of mass. We do it in the kilogram rather than gram because, like we would want in the meter, we want something that is, generally an approximation for like real-world objects. 1 meter is a decent size that you can have in the real world. It's not measuring protons. It's not measuring anything giant. But a meter is roughly something you can hold in your hands. We wanted to do the same with mass. Mass 1 kilogram is, if you're used to pounds, it's about 2.2 pounds. It's something that like an everyday object would have, just kind of a medium-sized unit. If you look at mass, if you look at a human, about 100 kilograms. If you want to take the mass of the Earth, you can also write that as about 6 times 10 to the 24th kilograms. Or if you want to go really small, you can, of course, write them really, really small as the hydrogen atom, which is 1.7 times 10 to the negative 27th. So it works very well. It's a nice medium type of measurement, and that's why we chose kilogram as the SI unit. The last one is time. So time has an interesting history a little bit to it as well. Before 1976, the standard of time was based on a day, with the Earth's rotation around the sun, the rotations of the calendar year. We looked up at a solar day and broke it into 24 hours. We took each of those hours, broke it into 60 minutes. We took each of those minutes and broke it into 60 seconds. 1 second of time, even though it doesn't seem like a lot, is our SI unit. Things can happen very slowly or they can happen very quickly, and the second is an appropriate unit that we can use for that. So that's how that became our SI unit. And you'll see it written out sometimes as second, or you'll see it as the lowercase s. But we did get that one a little bit more precise. If we want to take and look at higher precisions, we would take what we know as the atomic clock. This gives us very, very, very precise time measurements to a second. And the atomic clock, maybe you've heard of that, it measures vibrations of cesium atoms. Now again, why cesium? Well, it just worked. And you'll see actually down here, this is the best I could do for a rendition of a cesium atom being monitored and counted for the vibrations of a cesium atom. Now, cesium vibrates. It's a very predictable, it's a very stable atom, and it vibrates very, very consistently. So it's a little over 9 billion times that it will vibrate the radiation of a cesium-133 atom to give you a second. But again, these can be measured, they can be recorded. We're, again, working on something else that would be a little bit more precise for it. But the atomic clock is very, very accurate to the second, what we're using as a second. And again, second, if you're looking at how many seconds are in a day, well, that's 8.6 times 10 to the fourth. You can measure how many seconds are in a day. If you want to look at the entire age of the universe, it's 4 times 10 to the 17th. We can measure that. We can also measure things that are very, very small. We can measure duration for nuclear collisions. That's times 10 to the negative 22nd amount of seconds. So again, it's a very medium type unit that we're able to use, and that's why we have it for the SI unit. Okay, well, enough of that. Now that we know kind of what we're going to be measuring, how are we going to express these measurements? Well, we have a couple of different ways. We can use scientific notation, which is what I've been talking about. In order to do scientific notation, you just need to move your decimal point over and then give that representation to a power. So we'll see down here if we have 4,500 and we have to move the decimal place 3 places over to the left to give us a 4.5. This is the way we normally do it, is we give one integer out front followed by a decimal and the rest. 4.5, we have to remember it's times 10 to the 3 power so that we get back to our 4,500. This also works the same way for negatives. If we have something that is a very small number, we can just move that decimal point over to the right. If we move it to the right, it means we need to notate how many times we moved it to the right as a negative power in our scientific notation. You can also just give it a prefix. You'll see these a lot on your homeworks and in your book. Prefixes make things very, very quick and easy. You don't need to know all of these. There's just a table here that has most of them in it. The main ones that we're going to be dealing with are going to be milli. Milli is, of course, the scientific notation times 10 to the negative thirds. So you might see milli show up as just a regular M. You'll also see micro show up. Sometimes we'll have micro come in more next semester when you do Physics 2. You'll also have nano coming in next semester. I don't think we'll have a lot of nano this semester. But they follow these orders where you have 3, -6, -9, -12. And then after pico, even in Physics 2, you don't really get into femto, atto, zetto, iatto. You don't get into many of those. So you might have to reference back to this chart that a milli would be just an M. A micro is this U shape or this script M. Nano being N, pico being P. Centi is also fairly common. You'll see things written in like centimeter. It's just going to be a C that's located in front, and again, times 10 to the negative 2. Deci doesn't get used very much, not in our class anyway, so I won't worry too much on deci. These are for small things. Of course, when we go to the big things, the only one you're really going to use is the kilo. Right? It's for like kilogram. And it has a third power, times 10 to the positive 3. And its abbreviation we've already seen is the lowercase k. Now, next semester, Physics 2, electromagnetism, you might get into mega, which is a capital M. I don't know if we'll get into giga, but it would be a capital G. You notice these are all capitals and these are all lowercase, with the exception of the K, of course. And the rest of these we don't get into in our intro level classes, the Terra, the Petra, the Extra, the Zeta, and the Iota. We don't get into those. So you need to know these most common ones, and you'll see them on your homework assignments. You'll see them in the questions. You'll see them in class when I'm writing them down. So hopefully you'll get used to these just by enough experience with them. Okay, so we now know that we're going to be doing measurements. We know how to write our measurements. What are we going to be measuring? Okay. Well, there are lots of different fields of physics. Actually, there's much more in this flow chart here shows you. But we're going to be sticking to the classics. This is an intro course, so we should just be starting at the very, very basics. This will break off into classical, relativistic, and quantum. We're going to stick to the classical regime. And even classical has some different subtexts here. We have classical mechanics, electromagnetism, and thermodynamics, statistical mechanics. We will stick to classical mechanics for this course. This is a Newtonian physics. This is all about classical mechanics, which helps us out because I think classical mechanics is one of the easiest to learn. It involves everyday objects, usually things that you can pick up, usually things that you'll see or you'll know or you'll be able to relate to, like cats. And they're at speeds that we can observe. And even if we can't observe it, we can at least relate to it, right? We might have like a speeding train, or we might have a cat running across the street. The only thing that maybe we can't observe is maybe we'll have a bullet fired from a gun or a rocket taking off into space or something. And that's something maybe you have never observed, but at least you could relate to it. You can picture it in your head. You kind of understand what's going on with it. And it's not something that is, subparticle or moving so fast it is bending the fabric of space-time or any kind of craziness like that. Okay, it's just going to be larger objects, everyday objects. We're going to have soccer balls and people and boats and cats and, just normal everyday things. Electromagnetism is going to be your physics 2. That's going to be your next semester if you're taking this. Electromagnetism dives into a little bit smaller. It's still in the classical regime, but it goes into electrons and protons, moving through, creating electricity, adding magnetism, looking at fields, all sorts of other things. A little thermodynamics and a little statistical mechanics might be thrown into both of these, but this is, of course, going to deal with temperature and many body systems and those type of things like fluids and gases and how those things change. Relativistic is a very, very fascinating and fun field of physics, at least for me. Some crazy things happen when you approach it relativistically. When you approach the speed of light, some crazy stuff starts to happen, and it's actually observable, and it makes your brain hurt. Speaking of making your brain hurt, here's quantum. Quantum mechanics, quantum statistics, quantum electrodynamics, and quantum field theory. So these are the advanced courses, of course. You're going to want a good understanding of classical before you start tackling anything with quantum. So that's where we're starting. We're up here at the very top, classical inside of classical mechanics. So I will get you through everything you need to know for your intros. All right, so now we know what we're going to be doing. You can kind of guess where we're going to be at with physics. There's going to, of course, be some math. All right, so we're going to start right off with the math here. And what I want to first do is get down what these quantities are. Okay, so if you have two measurements, like say you have two lengths, you've measured a width and a height of something, and you multiply those two together, you'll get an area. Yeah, length times width, or width times height. You'll get an area. And so this is just the basic math. If you multiply all three, you'll get a volume. For instance, if you had like a cube type shape, you'd have length times width times height. If it's a cube and they're all the same, you'd have three lengths. And how we're going to measure that is we're going to look at its dimensions. So this would have two lengths for the area, length and width. This would have three, length times width times height. We'd have three lengths, so we'd have length times length times length, or we can have it as length cubed. If we look at the speed of something, how fast something's going, like if you get in your car and you go 30 miles per hour, you're doing a length over time. You're traveling 30 miles every hour, so you'd have length per time. Now, we don't use miles per hour, of course. We're going to use our SI units. For length, it would be meters, and for time, it would be seconds. Okay, so you'll see that show up down here below, meters per second. Just like volume is meters cubed, area would be meters squared. And then the last one that we kind of like to talk about would be acceleration. This would be if you change your speed. If you've got the cruise control set or you're traveling along at a constant speed, and then all of a sudden you speed up, you're accelerating. So that would be an acceleration. So this is length over time squared. So we'd see this as meters per second squared. Now, if you're used to the US customary units, you'd probably see square feet, cubic feet, feet per second, or feet per second squared. This doesn't happen very often that you usually see feet per second squared, but a lot of things will revolve around square feet or cubic feet. So you might be more familiar with that for the US customary units. And this is just a comparison. We are sticking to the SI units and all of the homeworks and everything else that's going on. So how does this help us? Why do we have to know all this? Well, it can give you a lot of detail when not a lot of detail is given. So if you have some type of a question, and one of the big challenges in physics is just understanding the questions. The questions are worded a specific way to give you clues on how to solve them. And if, for instance, the question states that there's a lake that occupies a space of 1,000 square meters, well, you know that meters squared is going to be an area. This is talking about the surface area of a lake. So just the top bit. It occupies this space is just the top surface area of the lake. Whereas if it said that it occupies a space of 1,000 meters cubed, then we would be talking about a volume, a three-dimensional volume. And that it's not just the surface area, but it includes all the water inside. So now it's a volume of water. So things like that, just knowing your units and what's going on in the problems, things like that can really help out and make things less challenging, less complicated. Okay. So we've got these SI units. We're going to have to be able to go ahead and convert from things that we know into things that we don't know. Okay, so we're going to do a conversion of these units. You may be given some in like feet or inches or miles, and we're going to convert those into quantities that are SI unit appropriate. So there's some things that I do expect you to know going into this course, and some things that are probably new. So some of the things I expect you to know would be that there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year, that there's 12 inches in a foot, and that there's 3 feet in a yard. So these are mainly the common ones that we see here. I'm assuming that you know these ones out. Some new ones that you may not know would be that there's 2.54 centimeters for every inch. There's 3.28 feet in a meter, and there's 1,609 meters in a mile. Now, some of these conversions will be given to you on exams and test questions and whatnot, or if you're doing homework, you're free to go ahead and look up these conversion units. But these ones, at least the expected to know on this side, you are expected to know these. All right, so if any of these are a little unknown, please do some checking. Okay, so that ends my slideshow right there. So what I want to do now is take these unit conversions, go to the whiteboard, and let's just do a bunch of examples on the types of questions that you're going to see on your first homework. Okay, so let's get started with chapter 1. We got unit conversion. I have some basic conversions written up here on the board in black. Some ones that you should know. For instance, for 1 year, there's 365 days. Every day consists of 24 hours. Each hour has 60 minutes, and each minute is 60 seconds. Some of the ones that you might not be familiar with are on the other side. Here we have 1 meter equal to 3.281 feet. A mile equal to 5,280 feet. And 1 kilogram is the same as 2.205 pounds. Okay, so we're going to start off with an easy question, and then I'll do a few more that get a little bit more complicated as we go. So our first example reads, how many feet are in 979 meters? Okay. So we always want to start off with the things that we know. Here we are given a number in meters, so that is, of course, where I want to start. 979 meters. And I want to do something to this in order to get it into feet. I want to do a conversion. Okay, so what I want is my answer to be in feet. Okay, something feet. Now, how do I get there? Okay, well, units, these conversion factors, can all be written as fractions that are equal to 1. For instance, if we put 1 year divided by 365 days, being that this is the exact same thing, we will get a unit factor of 1, a conversion factor of 1, and all of these are the same. Okay, they're all units of 1. 1 day equals 24 hours. So if I have 1 day divided by 24 hours, it's simply equal to 1. So we're going to treat these as fractions because they're equalities, right? If we divide over, we can treat them as equalities. I can do the same with meters. If I take meters and I just divide by 1, okay, it's still 979 meters. I haven't changed anything. Okay. So I want to take a conversion to get rid of meters and give me feet. Okay, so I go up there and I look to see, does any of them have that path directly? Okay, and there is one up there that does. 1 meter is 3.281 feet. That's the unit that I want to use. I'm going to write that conversion factor as a fraction. Okay, I want to write it as a fraction because I want a cancellation to occur. I've got meters up in the top in the numerator. If I could get meters down here in the denominator, meters divided by meters is 1. They'll cancel each other. So I'd like something in the bottom with meters. Okay. So in this case, if I grab that conversion factor, it says that 1 meter is equal to 3.281 feet. So the 3.281 is going to have to go up top. Okay. Now I've got meters divided by meters. This will cancel out the units. Meters over meters will cancel out all on its own. And now I've got the only units that are left in this are feet. Okay. So I'm going to go ahead and multiply across. I'm going to multiply the numerators, and then I'm going to multiply the denominators. And what do I get? I get 979 multiplied by 3.281. And what that'll do here is it gives me a feet. Now I'm going to do a little rounding here, but around 3,212 feet. Okay. And then of course this could be divided by 1, but anything divided by 1 is just itself. Okay, 3,281 feet. If you're wondering how we quite get this, is I can take any of these conversion factors. For instance, let's just take 1 day is the same as 24 hours. Okay. This is equal then to 1 because all I've done is just divide 24 hours to the other side. Divide both sides by 24 hours and we get a 1. Okay. I can also flip this around and say that 24 hours is equal to 1 day. It's the same thing. 24 hours is 1 day. 1 day is 24 hours. So both of these things are equal to 1. So I can write them in either form depending on how I want to do the cancellations. Here I chose to write meters in the denominator because I wanted meters from the numerator to cancel with the denominator. If I wouldn't have done that, if I would have flipped it by accident, I would have had meters multiplied by meters over feet. And our answer would have been square meters over feet, which is not what we were looking for. Okay. All right, hopefully that was a good example for the first one. Let's do one here that's a little bit tougher. All right, so let's try this one. Example 2. The first one that we did was kind of a one single problem where we just converted the 1 over. There are more complex ones where we can have to convert both units, convert 2 units. And this is an example of 2-unit conversion. So this example says that we need to convert 65 miles per hour into feet per second. Okay, so just like the first problem, I want to write down what I know and how I'm going to get there. So this says 65 miles per hour. So that is 65 miles for every 1 hour. Okay. So I can write that as 65 miles, and the per is always a division. It's 65 miles per 1 hour. Okay. So that's what I got started. Now, this isn't in the units I want to end in, so I know that I'm going to have to do some multiplication. I'm going to have to do some conversions. How many I'm going to have to do? Well, it's going to be a little harder problem, so it's going to actually be quite a bit. But I know that my answer should be in feet per second. Yeah, feet per second is what we're trying to get. So you can tackle these one at a time, okay? Depends on which one you want to tackle first. I'm going to go ahead and tackle miles first, okay? Being it's on the top, it tells me I need something with miles down in the denominator. I look up, I look at all my conversions, and I say, is there anything that'll get me from miles to feet in one go? Doesn't have to. Maybe it's more than one conversion. Maybe that's a tougher example. We'll do another. Is there anything that'll get me from miles to feet in one go? And there is. I have a conversion factor that says for every 1 mile, there's 5,280 feet. Okay, what is this going to do? Miles are down below, miles are up top. It is going to cancel the miles out. And now we are in feet per hour. We don't want to be in feet per hour, we want to be in feet per second. So we need to do another conversion. All right, feet is good. Now I got to get rid of hour. Hour is in the denominator, which means I want hours in the numerator. Okay. Now, how many seconds are in an hour? Because I'm trying to get to seconds. And there is no straight conversion to that one. Okay. If we only have one here that has hours, I don't want to go to days. I'd rather go down to minutes so that I can get minutes into seconds. So I see this is going to be a 2-part one. Okay. It's an easy 2-part one, though. 1 hour is equal to 60 minutes. Okay, what is that going to do? Well, it's going to cancel out the hours. Now we are in feet per minute. Is our only 2 units left, feet per minute. That's not where we want to be. We want to be in feet per second. So we need to do one more conversion. I have minutes on the bottom. I want to put minutes up top. Okay. What do I have that's in minutes? Hopefully something that'll get me into seconds. 1 minute, 60 seconds. So I have 1 minute equal to 60 seconds. This minutes will cancel with this minutes. And finally, the only units that are left are feet and seconds. Feet per second is the only one that is left. Okay. Now, if I do this out, what are we going to get? Well, you can stop here. You can punch it into your calculator if you want. Catch up and see if you did it correctly. But we should get around 343,200 feet for every 3,600 seconds. Okay, so that's 65 times 5,280 times 1 times 1 gets us here. 1 times 1 times 60 times 60 gets us 300 or 3,600. That's kind of a mess. Why don't we go ahead and just plug that into our calculator and get a nice solid number for it. And again, I'm going to round a little bit. Rounding is typically just fine in here. I'm not a big stickler on getting exactly perfect decimals and everything. So rounding in my class is okay. You should get an answer around 95. Being this is our final answer, and there's a lot going on, I usually like to put a box around it just to make sure. 95 is our answer. Make sure you got your units in there. Units are very important, and it shows that we are on the right amount of units. Okay, so that one is a 2-parter where you have an upper unit and a lower unit. Okay. Let's do another example of one that's even a little bit harder. Okay, our last example here, example 3, is probably a little bit tough. Takes a bit of work to get through, which is good. It's a good, tough example. Gets you used to it, really hones the skills, make sure you know what you're doing. So for this one, what we're looking for is the BMI. Okay, the BMI of a person is their mass over their height squared. Okay, it has to be kilograms over meters squared. So they're using all SI units for a BMI. The person of interest is 150 pounds. Okay. And the person who is 5'6" tall. Okay, so find the BMI, or what is the BMI of this person? We've got a couple of things to do. First, we've got a lot that's written down. We've got a lot of units that are there. We've got all sorts of extra things, like it doesn't specifically say feet and inches, but these are the common notations for feet and inches. So we've got feet, inches, poundage, but we're looking for kilograms and square meters. Okay, we've got a lot going on. When you have something like this and it seems overwhelming, like there's a lot that's going on it, break it all down. Just do little parts of it. Little parts are a lot easier to digest. Do little pieces of it and then put it back together at the end. That's usually where I would go on something like this and say, instead of trying to do this in one shot, let's make it simpler. Let's break it down. So I'm actually going to put it into two parts. One, I'm going to try and get that mass into kilograms. So for the first part, the top of it, I started with 150 pounds. Okay. And what I'm looking for is something in kilograms. For the second part, I know there'll have to be a conversion here, so we'll do this. For the second part, I am looking for a height. I'm looking for something in meters, but I'm given 5'6" and I want to get something in meters. And then what I'll do is I'll combine them. I'll plug in where mass is in kilograms, where meters is in meters. I'll plug them into the end. Okay, let's tackle the first part of the first problem. We have 150 pounds. I need to get it in kilograms. I go and I search and I say, okay, there's my good conversion units. 1 kilogram is equal to 2.205 pounds. So I want to make sure I have pounds on the bottom. 2.205 pounds, and up top is 1 kilogram. Okay, this is going to get rid of pounds on both sides and just leave us with kilograms. Plug into your calculator. Get used to using your calculator now. It's what you're going to be given on exams to use. Get used to using it. And let's see what we get for an answer on this. Okay. 150 pounds, going by that, looks like we're going to have roughly 68 kilograms. Hopefully that's what you got. Okay, 68 kilograms for their mass. Now let's work on their height. 5'6". Ooh. I don't have anything up here at all that is in inches to convert inches out. So how are we going to make this one work? Well, lucky for us, we know that how many inches are in a foot? 12, right? So this isn't exactly 5'6". We could rewrite this as 5.5 feet. Okay? You can always take the inches divided by 12. It's not given, but I'm expecting you to know there's 12 inches in a foot. We'll put that over 1. Now we need to find another conversion. We have feet. We need to go to meters. So I look up, and I see that we do have a unit conversion that goes from meters to feet. Here's feet, which means I want feet on the bottom. 3.281. And that's 1 meter. And now I can go ahead and do that math out. If we take 5.5 times 1, we get 5.5. If we get 1 times 3.281, we get 3.281. Let's take and divide those right off the bat, and we'll get around 1.7 meters. Okay, 1.7 meters. Move that a little closer. Okay, 68 kilograms, 1.7 meters. Now, the question was asking for the BMI. So what's the BMI equal to? Well, the BMI is equal to the mass in kilograms. So we'll have 68 And we're going to divide it by the height. The height was 5'6". We converted it to 1.7 meters. And this is where everybody gets messed up. We have to make sure that that is squared. Okay, 1.7 meters squared. So when you calculate this out, okay, what do we get for the BMI? Should get around 23.5. And the units are kilograms over meters squared, because we squared the entire 1.7, which was in meters. So the meters also gets squared. Okay, units can be squared as well. 23.5 kilograms per square meters. Is that normal for a person? If I had you go back and check and go, oh, think about this answer, does that make okay sense? It depends on what a normal BMI is. Okay, I don't expect you to know this, but normal BMI, it's great if you do, is around 18.5 to 24.9. Okay, a normal healthy BMI. If you like, check your own BMI. Okay, you know how high you are. You know roughly your weight, probably in poundage. Check your BMI for yourself. Okay. It's a great exercise to do. This is probably one of the more complex unit conversion ones that we'll ever see. Okay, hopefully that was good. 3 examples should hopefully be enough. You're going to do many more on your homeworks. Let me know if you have any questions.